So, we will continue our discussion with where we left in the previous lecture. This is the condition of plane strain indentation, and there was additional context to it or additional constraint to it, which is with frictionless interface. Where is the interface in this? When we look at this, this is our indenter. So, let me re-emphasize the indenter with this blue color. So, this blue color is our indenter, and this part of the material, this is this part of the drawing represents material, and this indenter is coming down, if you remember, and this is the field that we have assumed. There is additional one more triangle over here, and we broke it into we use the symmetry to break down the problem. So, now the problem is reduced to only this half. So, we are concentrating only on this part, and for this part we got up to this point. This is the hodograph for the above condition, for the above assumed field of deformation. So, as you can see over here, we have assumed equilateral triangle. So, all the sides are equal, and the V1, V2, V3 are at 60 degrees, which is what it comes to. So, their angle between these are 60 degrees, and these are our internal shear planes. So, this is also at 60 degrees, making this one also equilateral triangle. And if we know Vp, we can relate all the other velocities that we see over here with this velocity Vp. So, from the geometry we can construct hodograph, and from hodograph we can relate the various velocities to the Vp, that as we saw in the previous lecture. Now, we will continue with this. So, first question I have here is, what do we mean by frictionless interface? Frictionless interface means this is our interface. It means there is no friction at this point. So, if you keep indenting the material, if it needs to flow laterally, it can flow laterally without any work being done. So, that is what the frictionless interface over here means. Now, what is the implication of that? The implication is, now you see that there is a Vp, and this is the velocity of the indenter, which leads to velocity of the material V1 over here. So, there is a discontinuity in velocity, which leads to this OB, although it is not an internal shear, but there is some velocity discontinuity which is shown over here VOB. But since this is frictionless, therefore, no work is being done, and therefore, I have not denoted it by the star. Star are the ones, you remember, where work is being done. So, these are the internal shear, by default we have written it as star, and these are the V1, V2, V3, the movement velocity of the material. So, the material is moving like this, and since the outside is rigid, so there must be some shearing taking place there or work getting done over there. So, in effect we have 5 different planes at which work is being done, 1, 2, 3, 4, 5. These are the 5 different planes or regions where work is being done. So, next is again to write relation for external work, write relation for internal work, and then find a equation between them. So, let us start with the simpler one, which is external work. So, let us say that the pressure here we assumed, we have given it Pp is the pressure being applied. So, the external work rate will be equal to Pp times what will be the area? Area will be only, we have to consider only this part, W by 2. So, that is one dimension. What will be the other dimension? You remember we have stopped taking the other dimension, assuming that the geometry remains constant throughout. It is a plane strain condition. So, the third dimension we can ignore, and velocity Vp. So, this gives us the external work rate. what about the internal work rate? The internal work rate, if you remember, we have to sum it over all the 5 planes, and the shear stress would be the common factor, shear strength, and we have to sum it over all these 5 different planes. So, it will be K times So, this gives us the relation for internal work rate. Now, what do we need to do? We need to relate all the velocities that we have over here with the velocity that we know, which is Vp. Similarly, relate all the dimensions OA with the dimension that we know, which is W by 2. And given our geometry, you would see that it will be very straightforward. For example, OA, AC, CD, what are these? These are these dimensions. Now, this is an equilateral triangle. So, all the 3 lengths are equal. Therefore, we can say that OA equal to AC equal to CD is equal to AB is equal to BC, which is equal to how much? Will be equal to this length. This length we have seen is equal to W by 2. So, this comes out to W by 2. Now, what about the velocities? So, for velocities we will go to this plot. Again we see that the magnitude of all the velocities remains same. Why? Because this is again equilateral triangle. In equilateral triangle, all that this length represents the magnitude of the velocity in here, and since the length are equal, so magnitude of all the velocities are same, and this will be related to Vp. So, what is the angle over here? Now, if you look over here, there will be this angle would actually come out to be 30 degrees, and that would imply that if we take the velocities would come out to be so, in terms of Vp, it will come out to Vp by cos 30, which is equal to 2 by 2 Vp by root 3. So, now we have related all the velocities with the velocity we know, which is Vp. We have related all the dimensions, which are these lengths, to the dimension we know, which is W by 2, and so we will insert it over here, and we will see that our external work rate, which is Pp into W by 2 into Vp is equal to, now this will become K times all these dimensions are equal. So, this will become 5 times of whatever we get over here. The dimensions are equal to W by 2 and the velocities are equal to 2 Vp by root 3. So, we can cancel out our common terms, and what we are left with is Pp by 2k, which is the standard way we write it, equal to 5 over root 3. So, you see, even though it looked like a very complicated and involved problem, but whatever field we have assumed for it, we get a very simple and straightforward. We did not have to do much manipulation over here, and we get a simple relation of Pp by 2k, which is 5 over root 3, or you can write it as 2.89. Now, remember this is for one particular field, which is this particular field. We could have taken different fields, like we said that in the upper bound analysis you assume a particular kind of deformation field or a collapse field, and based on that you calculate the internal work rate. And so, if you take different kinds of field, you may find different values, and we are interested in the optimum. You remember last time we talked about optimum or best value of upper bound, which is the lowest. So, if you vary these things, it has been shown that the lowest value that you will get will be equal to 2.57. So, this will be the lowest possible value of all the upper bound analysis that you can do taking different kinds of deformation field, and this will be in effect your optimum or the best upper bound value. Best and optimum. Okay, so that is not all. Now that we have this P over 2K equal to 2.57, there is another important and interesting information hidden over here. You remember I said that this indentation is very similar to what we do in hardness. So, in hardness also you are indenting a punch, and based on the resistance the material shows, from that you measure hardness, and here also you are punching the indenter or the indent that is coming into the material, and based on that you get a value of P over 2K. So, this gives you a relation. P can be related to the hardness, K can be related to the material strength. So, this will give you a relation between hardness and the yield strength. So, hardness value that you obtain versus the yield strength of the material. Let us see how. So, what we will do here is we will use von Mises criterion and invoke K equal to y over root 3. Remember, this is something that we did at the very beginning of this course. So, you put it over here and you get what is y? Y is, remember, the yield strength of the material. What is P? Pressure required for indentation. In many hardness measurements, you directly use the pressure value. For example, in wicker hardness, you directly use the hardness value or the pressure value to quantify the hardness of the material. So, this P can now be written as HV is approximately equal to 3y, and you may remember from your mechanical metallurgy course, this is a relation that we often use. So, your yield strength and hardness that you measure of the material are correlated. Hardness is equal to 3y or yield strength is 1/3 of hardness. For example, let us now that we have put this equation, why not quickly do a simple example. So, let us say it is given that hardness value is equal to 150. Usually hardness will be given as number, but there is a unit attached with it, which usually is kg force per millimeter square. Now, if you convert it to megapascal, you will see that it comes out to 1500 megapascal. So, hardness has units of stress because it is pressure. So, stress and pressure have similar units, and it is usually, when you write it in number, a simple number, it has the associated or implicit unit of kg force per millimeter square. So, if you have hardness value given as 150, it means it is equivalent to 1500 megapascal, and therefore, yield strength will be HV by 3 equal to 500 megapascal. So, this is where you have a strong application of this relation HV equal to 3y. If you know just the hardness value, which is a very simple way to measure to make the measurement, you can extrapolate what will be the yield strength value of the material. Or on the other hand, if you have just the yield strength value, you can say or expect what would be the hardness for this particular material. So, this is still another importance of this upper bound analysis. Now, let us get to even another example for use of upper bound analysis, which will be in a quite different setup. This will be machining. Even in machining, you are actually deforming the material. Now, if you are doing the deformation, then you would want to know the relation, or you should be able to apply upper bound analysis, or at least this Hodograph, and be able to relate velocities, etc. So, that is what we will see over here. This is a plane strain machining. So, this is a workpiece, and this is the chip coming out. And VW represents the velocity at which the workpiece is moving, and somewhere here will be your cutting tool, which is usually characterized by parameter called Rake Angle. So, this will be your Rake Angle alpha. So, this is the setup showing machining. Over here, what you are doing is taking off some amount of material. So, this is the material that has been taken off. It is represented usually by A naught, also called uncut chip thickness. So, before cutting, what is the amount that is that thickness that is being removed, and after being removed, what is the thickness of the chip, because this is what is going into this. Remember, this thickness is not same as this one, although the drawing did not come out as nicely as it should have. If I draw it properly, then these two are independent. So, let me write over here, there will be some thickness for this, which will be called AC. And you would see that the construction is somewhat similar to the one that we drew at the very beginning of upper bound analysis. And if there is a velocity, so this is the velocity of the uncut chip thickness, and since the thickness here is different, so the velocity of the chip would also be different. So, let us call it VC. So, the material is moving. If I have to, the first thing that I need to do is look for symmetry, and if you can, and as you can see here, there is nothing in symmetry here that can help me reduce my problem. So, that part is gone. Second is to denote the moving parts. So, here are the moving parts. This is moving here, and when it crosses this line, it starts to move here. So, there must be a discontinuity here, which is your shear, where the internal shearing is taking place. So, this will be your, let us call it Vs, that is shearing, shearing velocity, and there will be an implicit angle over here. Let us represent it by phi. So, when we are talking about deformation during machining, these two angles become very important, alpha and phi, and another important factor becomes your ratio of chip thickness, the uncut chip thickness to the cut chip thickness, which is A naught by AC. Now, let us get to the next step, which is to draw the Hodograph. At this stage, you should be easily able to draw the Hodograph for this one, because this is example very easy to relate to the first problem that we discussed. and if you have to draw, you have to have an origin. So, the material, the original material is moving in this direction, it has a velocity v w, and let us say that for sake of argument v c, which is the chip coming out, is thinner in dimension than a naught, which is usually what you would have. That would mean that this will be moving at a much larger velocity, although in a different direction. So, this will be your V c, and what is connecting V w and V c? It is this shearing velocity. So, there will be V s. Now, what is known here is V w and some other geometry parameters. For example, what will be the orientation of V s? This is the V s and this is at angle phi. So, this angle is phi. What is the direction of V c? V c is at an angle alpha from normal. So, these are some other facts that we know about this, and we know all the angles, and we know V w. From here, if you were given to calculate V c and V s, it should not be very difficult, and as an exercise I will leave it to you to calculate V c and V s. I will just give you what would be the final form of the values, and as you can see I will write it in terms of all the known parameters, which is V w and phi and alpha. So, this is okay. So, this is actually shear, and the second one is and like I said, it should be very straightforward. Now that you know this geometry, overall geometry is known, alpha and phi are known, and you know V w. So, we are calculating, or we have to just represent V s and V c in terms of these. Now, here if you look at it, we have this angle phi, and I said there is another important parameter r. How do we get to know all this? How do we find out about this? In here from the geometry it looks like it is very straightforward, but it is not. First let me write down what is the relation for phi. Actually phi is given in terms of tan. So, tan phi is given by r cos alpha by 1 minus r sin alpha, where r is like what I said, a naught by a c, and it can also be written in terms of phi and alpha Okay, so, in practice what you do is you measure a naught and a c, you get r, and then you put r in over here with a known alpha angle, from there you get phi. Once you have phi, alpha and of course V w, then you can calculate V s and V c. However, now that we have reached up to this point, it is also useful to see how in machining we calculate some other important parameters when we are talking about deformation, like strain and strain rate. So, let us get to calculating the strain values in machining. So, our next aim is to be able to calculate strain in machining. For this, there was a model proposed by Merchant, and it is called Merchant's card model. It is a simple or a simplified way to calculate strain. As you can see, the way this deformation is taking place, it is not easy to calculate strain, but if you look at this model, it becomes, things become much lucid. So, let us say this is the uncut chip thickness and this is the direction in which the chip is flowing after being cut. And over here what we will assume is that this uncut chip thickness is nothing but a stack of cards. Okay. So, I will draw it as trapeziums. Actually rhombohedrals. So, these are the trapeziums where we have the cards stacked, which are representing the cards. Now, on to this side, after deformation what is happening? These cards are getting displaced. So, you see what this deformation is doing, in effect it is displacing these cards by this amount. So, if I had to explode this view, it will look like this. So, this is the displacement. So, let us call it delta S. Now, this delta S is being displaced for a thickness of this size. So, this is our delta Y. We have to calculate strain with respect to this. So, if you look at the geometry, if you were to write the equation for strain, it will come out to gamma equal to delta S by delta Y, because this is shear strain. So, we are looking at the displacement or the for this displacement with respect to the thickness of this rectangle. So, this is your delta S, which is the displacement with respect to the thickness, which is delta Y. Or if you write it in terms of the ABCD parameters, then we can write it as AB by CD, or further we can reduce it to AD by CD plus BD by CD. So, this is the exploded view of the strain that will be taking place in the chip when we are doing the machining and the chip is getting formed. Now, from here what are the other parameters? Again, let us put down the other parameters that we know over here. We know alpha, which is this one, we know phi, which is this one. So, now once you know all this, can you relate strain only in terms of the known angles phi and alpha? So, that will be an exercise that I will leave you with, that you should try on your own. You know this geometry, you have this is a horizontal line, these two are horizontal lines, and this is a perpendicular onto this, and this represents delta Y, this represents delta S, and these are the points. So, based on this, try to calculate gamma in terms of theta and phi. So, I will leave you over here, try to do it on your own before you get to the next lecture, and in the next lecture you would see me solving this. Thank you.